Okay, so let's start. Welcome to the webinar series. My name is Ismail Guvenc, and I'm going to be presenting today's webinar. And I would like to first acknowledge the support from IEEE Vehicle Technology Society for the sponsorship of this webinar series. And what I'm going to present today is our platform at NC State University called AERPAW. AERPAW stands for Aerial Experimentation and Research Platform for Advanced Wireless. It's a programmable experimentation platform that we are providing as a service for the advanced wireless and unmanned aerial system researchers. So this is accessible to you. You can access the platform remotely and then do experimentation. So I'm going to talk about many different things today. Initially, what I'm going to talk is I'll overview AERPAW, and I'll talk about the deployment areas. And it's a platform in progress. We are still working on finalizing the footprint and features of AERPAW. I'll talk about where we are right now. We are trying to wrap up our phase 2 by the end of summer. I'll talk about our phase 2 platform updates, and I'll also discuss other recent platform updates, including some research we have been doing over AERPAW, as well as what we are planning for the next phase, which is the last phase, phase 3. So this is the high-level overview. I'm planning to wrap it up in 50 minutes, and I'll see if you have any questions for me in the end. So I'll start with this Gartner hype cycle. I believe many of you may have seen similar hype cycles before. Gartner is publishing these hype cycle charts periodically, and what it shows is the technology evolution of any technology. So you can see on the y-axis there are expectations from a technology, and on the x-axis there are phases of the technology. So, and you can see many different technologies here. This is from 2021. It's slightly outdated. So, and you can see 6G and 5G over there, and you may also notice some other familiar technologies like Wi-Fi and low Earth orbit satellite systems, and maybe some others that are familiar to us as wireless researchers. And on the x-axis, we have the innovation trigger for a technology. So when there's a fundamental new technology, everyone starts working on that technology. There's a big hype. And at the end of that cycle, there is a peak of inflated expectation. So there's, like I said, there's a hype, and then after there's a saturation, people start moving on other technologies, and the expectation from that technology starts reducing. And there is thorough disillusionment is the third phase, which where the technology dips. But then there are the technology becomes more mature. There are experiments, there are tests, and people understand what can be done and what cannot be done with that technology. And then there is a slope of enlightenment, and there is a plateau of productivity. So all the technologies, they go through these different phases. So as academics, we love working on obviously the new technologies when there's innovation trigger, or even at the peak of inflated expectation. Today, many people are working on 6G. There are not many people are working on 5G, at least for the fundamental breakthroughs. The standard is already there. The reason, obviously, is everyone wants to come up with those high impact papers. No one wants to reinvent the wheel, because people want publications and citations, and it becomes more difficult to publish. If you are working on 3G or 4G, you won't be able to publish papers much anymore. But the challenge is many promising academic ideas or fundamental ideas that are proposed during the first phase, they may end up not getting tested for a long while, or sometimes they may not get tested at all. So testing and experimenting with those technologies, they are not, if you go with the fruit analogy, if you continue with the same analogy, they are not low-hanging fruit. So you have to invest a lot of time and effort to develop experimentation and testing mechanisms for especially for complex technologies like 5G and 6G and unmanned aerial systems. So it's a big effort. And continuing from there, you may also be familiar with this figure. It's a generic figure that I borrowed from elsewhere. You can see on the left-hand side, we have universities and national labs. They do discovery and basic research. On the right-hand side, there are corporations that do products and product development. And as we discussed earlier, in academia, the work is typically driven by publications and citations. There is this publish or perish culture. And on the corporation side, the whole work is driven by revenue. Publications are not that important. So in between, there is this value of death. So there are very interesting academic ideas, but many of those they don't get tested if industry is not interested in them, but they may be very promising ideas. To fill that value of death, we need programmable testbeds that are accessible to the broader research community. So there are people in academia as well who do individual experimentation and testing, but they are typically at very small scale on benchtop or really limited scope. But we need real-world, large-scale testing to be able to test those fundamental ideas. And one other thing I want to emphasize is the utility of those testbeds is they will help validate some models that are used in academic papers. Basically, when we have any fundamental research idea, we do simulations and we have to model certain aspects of the real world, like propagation conditions or antenna patterns or standard specifications. We typically abstract them, like we use Shannon models, Shannon capacity, or some other model. So there is this famous saying by George Box, who is a British statistician, all models are wrong, but some models are useful. So sometimes those models may be good enough to come up with conclusions, but sometimes we may be off from capturing the real world assumptions. And the conclusions that we may come up in fundamental research, they may not be accurate or they may be misleading. So these testbeds will also help validating such models. So to fill that gap, in United States, NSF introduced the PAWR program in 2018. It stands for Platforms for Advanced Wireless Research. And these platforms are large, almost city scale or large scale. Initially, they were meant to be city scale there, but they are typically very large scale outdoor test beds. And we currently have 4 of those platforms plus Coliseum, which is a channel emulator, a large scale wireless emulation platform. And the first 2 are Powder and Cosmos. They were founded in 2018. All of these platforms are still in progress, but Powder and Cosmos, they are the most mature ones since they have been funded earlier. They are close to finishing the regular project terms, project duration. So Powder focuses on software-defined networks and massive MIMO. Cosmos has a focus on millimeter wave and backhaul research in West Harlem, New York. In AERPAW, our focus is unmanned aerial vehicles and mobility. Obviously, all of these platforms, they are focused on advanced wireless, so we also have extensive wireless capabilities. And the last platform was funded June 2021, is in Iowa State. It focuses on rural broadband wireless, ARA platform. And we started AERPAW September 2019, and as of November 2021, we opened the first phase of the project. We opened it for external access with some initial capabilities. And by the end of this summer, we are looking into opening our second phase. We are releasing new features, we are releasing new footprint, new towers, new unmanned aerial systems. So I'll talk about all those in the coming slides. So what is our main motivation for AERPAW? And this is another slide that I like. I borrowed from Ericsson. Today, the operational mode for unmanned aerial systems is in this bottom left corner. We have manual control and we have visual line of sight. So the pilot has to see the unmanned aerial vehicle all the time with visual line of sight, and it cannot, obviously there are some other restrictions, cannot fly above 400 feet, a pilot cannot fly more than 2 drones, and etc. So these are part 107 requirements by FAA. But for the unmanned aerial vehicles to be successful or to be used in typical use cases like drone delivery, for example, they have to move to this top right corner. So they have to some extent, we have autonomous flights and visual line of sight operations today. But what we really want is drones flying much longer distances in an autonomous fashion, like they can deliver you your food, for example. There are already companies that are testing those. But to achieve this beyond visual line of sight flights, you really need a reliable link, wireless link. And with AERPAW and advanced wireless research capabilities, we are looking into filling in this gap, so to unleash the true potential of unmanned aerial vehicle system use cases and applications. And it's again, we are leading this effort at NC State. It's a platform hosted by North Carolina State University. And there are 5 other institutions who are part of this project. And we are also partnering with municipalities and North Carolina DOT. So what are the unique features of AERPAW? We share some of these features with some of the other power platforms, but we also have some unique aspects to AERPAW. So let's start with the radios. So at AERPAW, we have programmable radios that are deployed at scale. These are typically software-defined radios that are from NI, National Instruments, USRPs. We have many different types of USRPs. So we have smaller and larger USRPs that can implement 4G, 5G, or other standard-based or custom technologies. So in addition to those, we have some other commercial radios as well. We have LoRa gateways, LoRa sensors. We have an Ericsson Network that is capable of 4G and 5G transmissions. It belongs to AERPAW platform. It's a Release 15 compliant 5G network. We also have RF sensors from Keysight, and with these radios we can transmit custom waveforms. So these radios are pretty much, they are shared, they are similar in all the other power platforms as well, at least the software-defined radios. But what we are unique with AERPAW is we carry these radios at programmable vehicles, which are unmanned aerial vehicles or unmanned ground vehicles. And these radios are attached to these vehicles, and these vehicles, they can be controlled precisely and in a repeatable manner. So, so when you do an experiment today, with the vehicle, you define the waypoints about where the vehicle is supposed to go. And then when you repeat it again a week later, the vehicle is going to go through the same exact locations in the field. So you have a repeatable platform to test your new algorithms. It can be for handovers or interference management, and you have a repeatable environment to test different algorithms and technologies. And I also have autonomous here. In addition to, when I say repeatable, you define waypoints. So you say the vehicle that you are going to go to XYZ points, or whatever number of points you want the vehicle to go. The vehicle goes to each of those points one by one, and it comes back to the initial location. But you can also program the vehicle to decide where it should go next itself. For example, you can program the vehicle to stay within the coverage area of a tower. So it observes signal strength from a tower, And then if it realizes that the signal strength is reducing, it may decide to go in a certain direction so that it stays within the coverage. So it's all up to how you program the drone. Or you may program to localize a signal source. Actually, I'll talk about the competition that we are running in the platform in the coming slides. We have a relatively large outdoor footprint of towers in 2 different locations in Lake Wheeler and Centennial campus. I'll talk about those in the coming slides too. What is again unique to AERPAW is we have a cloud-based development environment for what we call as a canonical experiment. So these are experiments that are typically with software-defined radios. This is a digital twin with the popular term. So you can program all your experiment, including both the radio and the vehicle software, in the digital twin, which is a twin of our real-world testbed. So we have the towers, we have the unmanned aerial vehicles, we have the radios at the same locations in the digital twin, and you program the real software for both the radios and the vehicles in the digital twin. And once you finish programming, you're actually done with your experiment. So to move that experiment to the testbed, we take that software from you and we deploy it in the testbed as it is. So you have programmed the real software that will run in the real world environment. So that's also a unique feature of AERPAW, because we have smoothly integrated this digital twin to our testbed environment. So we have containers that you program in the digital twin. We take those containers and we deploy in the testbed, and that digital twin is capable of all the waypoints and autonomous navigation that I explained earlier for vehicles, as well as the radio. So the drones, they communicate with the tower or each other through the emulation environment. We have spectrum licenses from FCC. For now, low band and mid band. We are working on getting our millimeter wave spectrum licenses, and we have expertise with pilots and waivers. So we have many Part 107 pilots who will fly the drones for you, so you don't have to fly the drones. So once you develop your experiment in the digital twin, we take that from you and our pilots do the experiment for you. And this slide shows the deployment footprint of AERPAW today and what we have in each of the outdoor fixed nodes. Fixed nodes are, or you can think of them like towers or base stations. So we have 2 main areas for AERPAW. The first area is on the northern part of this map. We have the AERPAW Centennial campus. Unfortunately, we cannot fly drones in the Centennial campus site today. But you can do experiments between the fixed nodes, or you can carry portable nodes. I'll talk about what's a fixed node and a portable node soon, but you can carry them in a cart, or you may also support experiments with unmanned ground vehicle. So we have 3 fixed nodes in Centennial campus, and we have 3 additional nodes that only have Facebook telegraph radios. So in each fixed node, we have software-defined radios. We actually have 4 software-defined radios, which are USRPs. They are connected to antennas, and then you can program them to communicate with the other fixed nodes or with some portable node. And on the southern part, we have this Lake Wheeler Field Labs, which also belongs to NC State. So it's an agricultural research farm. And we have 5 fixed nodes in Lake Wheeler Field Labs, and they're all towers. They can be configured to be either 30 feet or 60 feet. We typically keep them at 30 feet height. And they again have software-defined radios or USRPs, each of them. But some of them, they have additional equipment, like this red fixed node you see here. It has an Ericsson base station, which is a 4G/5G standard compliant full commercial base station. We have LoRa gateways in all the 5 fixed nodes. Actually, in 2 of the fixed nodes here, we also have LoRa gateways. We have RF sensors in 3 of those fixed nodes. These are RF sensors from Keysight that they can do spectrum monitoring or signal classification or even signal source tracking and localization. These fixed nodes, they can communicate with each other, or they can also communicate with so-called portable nodes. So portable nodes are, as the name suggests, they are portable and they are meant to be carried by vehicles. And in AERPAW, or vehicles we have 2 different types of drones. LAM is a large AERPAW multicopter, and SAM is a small AERPAW multicopter that can carry different sizes and weights payloads. And we have an unmanned ground vehicle and a helikite. And the portable nodes can be attaching any of these vehicles. We have multiple different types of portable nodes as well. So some of the portable nodes, for example, they cannot be carried with the SAM because they are too heavy. The portable nodes have, at least the large portable nodes, they have a small USRP. You can program the USRP again in our digital twin, and that is connected to an Intel NUC computer that runs Linux and containers, which will run the containers that you develop in our digital twin. And for this small portable nodes that are carried by the smaller UAV, you can carry mobile phones or LoRa sensors or 5G dongles. I'll talk about those a bit more later. And with this platform, I listed a bunch of application examples and research examples here. You can do research related to advanced aerial mobility. For example, you can define geofences for air corridors, and then you can look into communication performance. You can look into delivery, smart agriculture, search and rescue, localization, and you can look into, you can implement 4G, 5G protocols. We actually have many example experiments that the experimenters can start with. I will talk about all those in the coming slides. Autonomous trajectory optimization, and even counter unmanned aerial system type of research. And a couple of photos. This shows our Lake Wheeler 1 tower that we see here. And the drone flying nearby. There are actually some additional equipment on top of the tower here. This particular photo does not show the Ericsson network here, but you can see the antennas that are connected to the software-defined radios in this enclosure here. There are 13 antennas at the top, and then they are connected to the SDRs through these cables. And there's a separate Ericsson network, 2 sectors for 4G and another 2 sectors for 5G that are also attached to this tower. And this slide shows our LAM, large AERPAW multicopter. It is designed and fabricated fully at NC State, and you can actually, if you wish to replicate the same drone, we have the blueprints, and you can do the same drone yourself. And you might see the portable node that is attached to this LAM at the bottom. So you can detach it and put it to the unmanned ground vehicle. I'll show you in the next slide. But you can also notice many different wireless links that are coming to this drone. We have GPS receivers, we have RC antennas, there's a safety pilot that is monitoring where the drone is flying. The pilot is not really controlling the drone in AERPAW, so it's just making sure that everything is safe. So the drone flies based on how you program the drone to fly. If you define waypoints, the drone is going to go to all those waypoints, and the pilot is just going to watch and make sure that everything is safe. And the pilot can take over if the pilot realizes there may be a safety hazard and then may bring it down. But otherwise, you are in charge of what the drone does. And you may also see a cellular modem here. This is connected to AT&T's 4G network. This is not for the experimenter. This is for AERPAW platform operations. We are continuously monitoring what the drone is doing, where it is going, and if it's transmitting in a prohibited frequency or not. And we can take over through this backhaul link that goes to AERPAW's backplane. And what the experimenter is concerned is experimental transmitter and receiver. So the particular portable node you see here is a SISO portable node. We also have a MIMO one with 2 transmit and 2 receive antennas. But you can see these antennas are separated enough so that there's a limited coupling between them. And then you can communicate through these antennas with other vehicles or the ground fixed nodes. And you can take this portable, okay, we also have a small AERPAW multicopter, and it has a much smaller portable node. You might notice that it's carrying below the drone, but it cannot carry software-defined radios, at least at this time. It carries mobile phones or sensors or 5G dongle, as I mentioned earlier. So this SAM, it flies for about 85 minutes, and LAM flies for about 35 minutes. And you can take the large portable node and attach it to an unmanned ground vehicle, and it has the same interface to interact with the UGV, and you can again define waypoints. You can make the navigation autonomous based on signal strength observations. The unmanned ground vehicle may decide what to do. So it's basically detachable, and it's plug and play. So you can take it and attach it to yet another drone and run your experiment. And you can have multiple UAVs and UGVs as well to use in your experiments. The way that an experimenter interacts with AERPAW is shown in this slide. So as an experimenter, I'm not going to go through all these things. You can go to our user manual and website, and these are all these steps are described in detail in our user manual. But in summary, as an experimenter, you first come to aerpaw.org, and in aerpaw.org there are 2 links. One of them is to our user manual that describes how to use the platform. We are still making some updates to integrate phase 2 features of AERPAW to our user manual. But there's another link that points to experimenter web portal. So you first log into the experimenter web portal through CI logon. You have to have your institution listed under CI logon, and many of the institutions in US and even outside of US, they are listed there. So you are authenticated first through your institution, and then you connect to our experimental web portal, and then you start defining your experiment. You say, to do my experiment, I need 2 fixed nodes, I need 2 portable nodes, and 2 UAVs. And then once you specify your experiment, then you get assigned containers in our development environment or digital twin that correspond to each of those resources. So you may have a container for one fixed node, you may have another container for another fixed node, and you start with certain sample experiments. So you can start immediately from an already tested and operational experiment, for example, for 4G LTE fixed node communicating with a drone when it's flying in a certain trajectory. So you can start immediately from a tested experiment. And then once you get assigned the containers, you can start working with them immediately in your digital twin. You can define your waypoints. You can modify the radio scripts. You can, for example, test a different power control algorithm or different scheduling algorithm. And then once you are ready, you execute your experiment first in the emulation environment or the digital twin. We have a very simple propagation environment that I'll talk about in the digital twin. It's basically a free space line of sight plus ground reflection. So we don't do any ray tracing. We have a simple model that calculates the ground reflected path. And then you can obtain results with the real software, real radio software, and the real vehicle software in the digital twin, and you can observe, for example, RSRPs for LTE or 5G and how they change with the vehicle's location. And once you are happy with what you see in the digital twin, then you can ask us to deploy that software as it is in the testbed. So you can see the top part here is AERPAW virtual node. So this is the digital twin that I have been referring to. The bottom part is the testbed, AERPAW radio nodes. So the top part is really fully softwareized environment in the cloud. At the bottom, we take those software and we deploy in the testbed environment. And then once you move the experiment to the testbed phase, the AERPAW operations team, they will schedule the experiment when they can run it. So we have to obviously we have a pipeline of other experiments. We have to queue your experiment, and we also have to look into days that it doesn't rain and it's not windy. We go to the field and we deploy your experiment. So you basically have to wait until we execute your experiment. Once we execute the experiment, we move it back to the development stage and we provide you back the data that comes from the experiment. You can take the data and then you can see how it compares with what you observed in the emulation environment, and then you can decide whether you are going to refine your experiment further, or if you're happy with your results, you can take those data and you can publish your paper. And what I just described here is what we call is the program it yourself type of experiment. So maybe just to back up a little bit. So what I described is in the operational sense is AERPAW is a batch mode facility. So experiments are first developed in the virtual environment, and then they are submitted to the AERPAW ops for execution in the physical testbed. So you develop it and then you give it to us, and then we deploy it in the physical testbed. And this is the program it yourself type of experiment. So you, especially if you're a researcher funded by NSF, you have free access to AERPAW, at least at this time, for using the program it yourself type of experiments. And when I say program it yourself, I refer to the digital twin. So you can program all your experiment in the digital twin and then we deploy it. But not all experimentation modes in AERPAW are program it yourself. We have other experimentation modes. One example is limited live access for key site RF sensors. You can, and soon we are adding LoRa into the same experimentation mode. With these two different equipment, you basically do remote access to a computer, and then you have real-time access to control key site RF sensors or the LoRa gateways and sensors and pull data from those devices. We also have more complicated modes like AERPAW as a service. If you have a complicated NSF project and you need our help to tailor certain experiments, and then we can charge some fee to program the experiments as to fit into your needs. Or you can also bring your own device and we can integrate that. Again, for this may be a bit more complicated. We may not be able to support all different types of equipment. You can send us an email at airpawcontact@ncsu.edu. And if you have an NSF funded project, NSF also provides supplements up to 50K each year to support research on power platforms, and AERPAW is eligible to support such supplemental projects as well. So let's look into some phase 2 platform updates. So what I presented so far is AERPAW at a high level. In the coming slides, I'm going to tell you where we are and where we are planning to be by the end of this summer when we release our phase 2 general availability features. So at this time, we have 8 fixed nodes and 3 Facebook Telegraph nodes that are fully deployed and available. as I have shown earlier in the deployment map. We have 3 upgraded large AERPAW multicopters. They have new yaw control that is based on GPS, new battery mounting system. They have cameras. They are RTK enabled, 1 centimeter precision on trajectory, so it's very accurate. We have 4 upgraded small AERPAW multicopters. So with LAMs and SAMs, we have 7 drones that we support today in AERPAW. And there's SAMs, they had certain updates with RTK and cameras. We have 2 rovers. One of them is upgraded with the RTK, and it can go in all terrain. So this is how our new rover looks like. We have 6 upgraded large portable nodes and 4 small portable nodes. So today we have 10 different portable nodes that we can deploy in real experiments in AERPAW. So if you want to do experiments in the digital twin, you can also pool all those resources in your experiment in the development environment. AERPAW supports this digital twin that I have been referring earlier. Essentially, digital twin has containers. We call them EVMs, experimental VMs, but they're essentially Docker containers. And they can be for the portable node or for the fixed node, and there can be multiple of those. If you have multiple fixed nodes and multiple portable nodes for multiple UEs and multiple base stations. And if it's a portable node, it runs 3 different scripts. These scripts are traffic generator, radio software, and vehicle control software. And if it's a fixed node, obviously we don't have vehicle control software. We cannot move the fixed node. So the vehicle control application, it basically, you can define the waypoints and tell the drone or unmanned ground vehicle where to go. And traffic generator, actually, if I click one more, so the vehicle control application, you have an interface to Q ground control. You can see on a Google Earth environment, you can place the waypoints on where the drone is supposed to fly. Traffic generator, for now we support ping and iPerf, and radio software, we support many different types of open source SDR software like SRS-RAN, OAI, GNU Radio, and a series of Python scripts. And our emulation environment that you see at the bottom, it basically takes and passes IQ samples from each of the portable node and fixed node to the other portable node and fixed node. So this is a fully softwareized environment right now. We don't have any hardware. We don't support USRP hardware here, but it's the real USRP software that's running in the background. So we are bypassing the hardware, and we are not able to capture the hardware limitations right now. We are actually working on a sandbox for phase 3 that we will integrate to capture also RF front-end impairments and other impairments. But the nice thing with this is, since it's fully software-based, it's very scalable. So we may have 50 different experimenters running experiments simultaneously in our cloud, and they can be programming their own radio and vehicle software in parallel, and we can support such experiments. So it's very scalable with larger number of users. So the block you see at the bottom, to open that a little bit more, like I said, it forwards IQ samples between different radio nodes. Currently, it supports free space and two-ray propagation model. It can support many different frequencies. Our default frequency for AERPAW is 3.4 gigahertz for SDR experiments, software-defined radio-based experiments. We have experimental licenses to deploy those experiments in outdoor testbed. If you are just interested to do experiments in the digital twin, you can use whatever frequency you want because you are not radiating any signals. But the main idea is, once you develop your experiment in digital twin, we will take it as it is, and then we will deploy it in the testbed. So we use 3.4, and 900 megahertz is another band that we support right now. up to 100 megahertz of instantaneous bandwidth, multi-rate processing. We also have different antenna patterns, and it can support different noise levels as well. And like I said, we are working on integrating a channel emulator that supports real hardware in phase 3. We use a Keysight PropSim channel emulator in the sandbox. And this slide shows the experiments we are offering you as part of our phase 2 general availability to start with. These are all tested and they work in the emulation environment. We are working on finalizing some of the testing with the actually the 3 that are pending right now that we are making some final updates are 5G SRS RAN and 4G handover and IQ sample collection experiments. But other than those 3, the other experiments, they are all tested in our emulation environment in the digital twin. We fly drones, they communicate with the fixed node, and you can plot results. So you can start with them, or you can also, if you are willing to do, you can also bring your own experiment to the development environment as well. And if you click each or any of these links, the slides will be available, and these are also available in our user manual that you can access from airpaw.org. So you have a description of the whole programming steps for each of these experiments. So all these experiments, they are available in the digital twin, except the Keysight RF sensors that I have mentioned earlier. So this is slightly shifted. So Keysight RF sensors, they are limited live access. You have to access a remote log into a computer, and then you have access to our RF sensors. And how to use that limited live access mode is also fully explained in our user manual. You can read if you are interested. So just to show you how we have been evolving from phase 1 to phase 2. So in phase 1, which we released in November 2021, we had very simple trajectories, just a linear path or a zigzag path. So we only had one fixed node in phase 1 in Lake Wheeler, in the area that we fly the drones. Right now we have 5. We have a much larger deployment footprint. So in phase 2, we are doing flights in a much larger geographical area. So you can see in this particular flight plan, we are flying nearby 3 different fixed nodes, and in this particular one is flying across all the 5 fixed nodes. The blue and green boundaries that you see, these are actually the geofences. We do not allow the drone to fly outside of this geofence. There may be small buildings, or we don't fly over buildings or people. But any other place, you are allowed to fly the drone. And you can define your own flight plan as well, but we recommend that you use the flight plans that we offer, and then you may have access to other people who have used the same flight plan, and then you may compare your experiments with other people's results. I mentioned about the repeatability. I have about 6 minutes left, and I hope to leave 10 minutes for Q&A in the end. So I'll try to be faster in some of the remaining slides. So repeatability, like I said, whenever you run the experiments again, it follows the same exact path, and the pilot is just a safety pilot. So it's your experiment or your program that flies the drone. And then you can compare results between emulation and the real-world testbed. And what you see on the right is what we provide to the experimental. So there's a vehicle application on the top that you program either waypoints or how the drone is supposed to move based on an autonomous navigation algorithm. We have our own AERPAW vehicle library, and if you wish to go even deeper, there is the open source code that you can even program, but we we do not allow, I mean, we have our safety procedures that we want to make sure that all the experiments are safe. So I'll just show that we have key-site arrest sensors and LoRa gateways deployed in all these different fixed nodes in Lake Wheeler and Centennial campus. And key-site arrest sensors are generally available now. You can remote log in to the computer and have access to interact with them. LoRa, we are going to make it generally available in phase 3. So we have deployed all the LoRa gateways. We are actually deploying sensors in the field, and we also have plans to fly a LoRa gateway at a drone in phase 3 as well, to be able to collect data from sensors at the drone when the gateway flies. And we have the Ericsson Network, as I mentioned earlier. It has 2 LTE sectors and 2 5G sectors, and the bands are 3.4 gigahertz for 5G and 1.7-2.1 gigahertz for LTE. Currently, the way that we opened the Ericsson Network to our external users is we fly a coaxial modem at the small AERPAW multicopter, and we have scripts that keep logging certain KPIs from the base station, both 4G and 5G. So you can program the drone. So what is available to you as an experimenter to program is where the drone flies. So you can program the drone to fly in all the locations that you want to collect the data. You may want to collect, for example, the antenna pattern across a base station, or you may have an autonomous navigation algorithm that you want the drone to fly in a certain pattern based on what it observes. But what we are doing at the portable node is just logging KPIs like ISRPs or packet error rates or latencies, and we have a list of what KPIs we are logging in our website as well. So if you go to our user manual, we have a description of how you can use this Ericsson Network experimentation profile. One thing we are working on for making available in phase 3 is a millimeter wave SDR capability that will also be carried at the drone. We published a paper recently in actually last month in one of the Infocom workshops. And we also provide some measurement results there in an indoor environment. So we are working on integrating this to AERPAW drones for our phase 3. So this is based on a Cyverse phased array platform. You will be able to control the beam patterns and beam directions, and you can do some interesting experiments, hopefully before the end of phase 3. And we are one of the AERPAW is one of the FCC Innovation Zones in the United States. We have all these frequencies in our innovation zone, but we have to explicitly apply for experimental license if we want to support any experiments in these innovation zone bands. So if you are in an innovation zone, if you have an innovation zone frequency, it doesn't mean that you can immediately run experiments in these bands. We still have to go through certain procedures, but it's an expedited process. So our default bands, like I said earlier, for SDR experiments is 3.3 to 355 and 902 to 928. We are actually not doing any experiments 345 to 355 because it is now being used by cellular operators, so we are below 3.45. We are working on new experimental licenses. We want to go all the way down to 3.1 gigahertz. And we are also working on getting new experimental licenses for 28 gigahertz and C-band of about 5 gigahertz for drone experiments. I'm already out of time, but I'm going to show very quickly if I'll leave less than 10 minutes for Q&A, very quickly some sample experiments. So this is from a typical experiment profile. Or this trajectory is one of the typical path plans that we use. We call it a zigzag trajectory, and we have this at multiple altitudes from 30 meters all the way to 110 meters. In this experiment, we are running the IQ sample collection software, and we are collecting IQ samples from the LTE node B that is being transmitted from a USRP. And what we do with this experiment is we collect IQ samples from the LTE node B. Again, this is a USRP that is transmitting at 1.4 megahertz or bandwidth at 3.4 gigahertz. And then once you collect the IQ samples, we go to MATLAB's 4G toolbox, and then we post-process all those IQ samples. And as you can see here, these are data collected at 5 different altitudes. You can use the MATLAB's 4G toolbox to obtain the resource grid. If you are familiar with LT, you can see all the common reference symbols, synchronization sequences, broadcast channel, and you can see at 2 different SNR levels. So the bottom figure here is actually at a much lower SNR, but you are still able to extract RSRP, for example, from these measurements. And then you can plot RSRP as a function of trajectory, as a function of time or location. You can fit different propagation models, and you can also do spatial analysis. But for this research, what we are looking at is we are looking into interpolating the coverage across the whole 3D volume based on RSRPs that we measure. And we actually have a 5G version of this as well. We collected IQ samples using our Helikite platform, and then you can go to the 5G toolbox of MATLAB, and then you can post-process. You can see the SSB block here, and then you can calculate RSRP as a function of time. So the figure on the bottom left here, it shows the altitude of our Helikite that we flied close to Raleigh downtown. And you can see that the RSRP in many different PCIs, they follow very similar pattern. As we keep going high, you observe stronger signal strength or stronger RSRP from the base stations, because you are starting with line of sight with those base stations. And yeah, so this is based on 5G, and you can repeat. Actually, you can do similar experiments also in the emulation environment. We have both 4G and 5G software-defined radio-based profiles, so you can collect samples and post-process those in MATLAB later. And we also provide you the post-processing scripts in MATLAB. So we have the data. If you're interested to use our own data, we have data posted in our website, or you can collect your own data and then you can use our MATLAB scripts if you're interested to obtain related results. And this is another result from this is for spectrum occupancy at different altitudes. We collected spectrum measurements from a large number of bands, both 4G and 5G, and then we look into how the spectrum occupancy changes with respect to altitude. So, and we publish all these papers. So if you go to Google Scholar and search AERPAW, you can find all these papers if you're interested to go deeper. Very quickly, just to show what kind of insights can we extract from these measurements. This one just focuses on, I showed here a couple of different bands. We have many other bands that we collected data, but we focus on band 12, which is used by AT&T and T-Mobile in the United States. And on the left, you have the uplink, on the right, you have the downlink, and top is for the rural environment and bottom is for the urban environment. And what you see here is the spectrum occupancy. It becomes more and more occupied as you keep increasing your altitude. But in the rural environment, the spectrum occupancy increases more gradually. But in the urban environment, you are obstructed by buildings, so you're more isolated, you can see. And this is very similar pattern in many of the bands that we checked. So as soon as you go above the buildings, your spectrum occupancy starts increasing quickly. And And there is a lower spectrum occupancy, especially in rural environments when you compare with urban. Again, we have many different bands. We see the similar pattern. And there may be spatio-temporal pockets of opportunities that you can reuse. And that's not only dependent on the spectrum, that's also dependent on altitude. So this shows the opportunities for spectral reuse that may be altitude dependent, and there are similar observations for 5G as well. And we have a data repository that you can go to airpaw.org, and then you can access to our data. We have a series of tutorials that are video recorded. You can go through these tutorials to learn how to program vehicles, how to program different sample experiments, and then you can execute the same experiments in our digital twin. And we have a competition series. All of these are very accessible through airpaw.org. We are accepting applications till June 15th. You just need to register. We are actually planning to extend this registration deadline even further. This one is for localizing a signal source on the ground, and you will program this in our digital twin. And we have had a nice workshop in May 8th to May 11th. If you go again to airpaw.org, we have a link to the workshop website, and there are a lot of educational materials that you can access on our website as well. And this is probably my last slide. We have a series of exciting features that are coming up in phase 3 that we are planning to start after August this year. We will have new example experiments with 5G and multiple UAVs and higher speeds. We have a series of other non-ASTR experiments coming up as well. And we are working on integrating drone operations centers to expedite our operations too. So with that, I'm going to stop. I know I overused my Q&A, but we still have some time for question and answers if there are any questions from the participants. Let me see. Are there any questions? Yes, questions?
Yes, I am Hisham Badawi from Egypt. Thank you for your nice presentation. I would like to express my sincere appreciation for your presentation. But I'm asking about the opportunity of how to manage the interference, especially in the vertical direction between the UAV and the original terrestrial access network. Thank you.
So just to repeat your question, so you're asking how to manage.
How could you mitigate or adapt the interference between the coexisting terrestrial access network, such as 3G, 4G, LoRa or something? Or you can integrate both of them on the same fusion center?
Great question. So maybe just going to my slide here. So as far as the experimenters are concerned who are using AERPAW, we are using bands that are not used by the commercial operators. So we are not interfering with the other operators. But if you want to test interference yourself, you can set up an experiment where there may be one fixed node, which, for example, mimics a commercial LTE base station, and you may have another fixed node which may be communicating with the LTE. So you can set up an experiment with two fixed nodes and one UAV. UAV is flying and communicating with its own base station, but in the meantime, it may be interfering to the other base station. So you can test, for example, inter-cell interference coordination mechanisms in LTE or power control. So as maybe you might be familiar with the interference concerns from UAVs is major because it's at a high altitude. It has line of sight with many towers. So I guess that was your concern that you wanted to raise. But you can experiment different mitigation techniques. So there are techniques in the literature that are published in simulations or analysis, and they can be experimentally tested in AERPAW. And you can do that initially in the digital twin. You can, in a simple propagation
Something looks like
environment.
index modulation or something to identify the UAV network from the existing terrestrial network to eliminate the interference as much as possible.
Sorry, can you repeat? I missed.
I mean that you may use some sort of coding or index modulation in order to distinguish between the UAV network and the other interfering network.
Yes. Yes, so depending on what you exactly want to do, yeah, you can. So if you have anything that you simulated in MATLAB, for example, you should be able to carry it to AERPAW as long as there is an open source software that supports. For example, if you are, it depends on your waveform, right? If your interfering network and your UAV network, they are both using LTE. So there are open source software that you can deploy in AERPAW with LTE. Same for LoRa. If you have LoRa, or you can mix and match. So the interfering network may be LoRa, the other may be LTE, assuming they are using the same frequency band. So you can test all those different combinations. So how you detect this is basically a research issue, depending on what waveform is used and what approach you are implementing. Thank you. Each type of, okay, there is a question on the antenna. So we use dipole antennas at the UAV at this time, both at the UAV and at the base station. And if you go to our website, there are data sets, and we actually have characterized the antenna patterns both at the UAV and at the base station in an anechoic chamber. So we also provide you the antenna patterns if you're interested to analyze the effect of antenna pattern, for example, on coverage. But for Ericsson Network, we have a commercial 5G antenna at the base station side, and it has a much better antenna gain. On the UAV side, we use coaxial modems, so we use their antennas. Another question, is there an interest from that universities may use to express interest in using research platforms? Is there a document that shows the path a university may follow in engaging and collaborating with AERPAW? So if you go to our website, I would recommend you to read our user manual. There is a link immediately. I think that's the second tab at aerpaw.org. From the landing page, if you read through the user manual, it gives you the process and the workflow, how you can access AERPAW. I'm wondering if, in addition to the use of UAV as a user, has it been experimented to be a UAV base station? We haven't tested, but we are pretty sure. We are confident, actually. We have been talking about using it as a base station for a while. But yes, so you you can deploy UAV as a base station, and it should be it should be able to support users on the ground, and that can be tested in our digital twin first. So we were planning to experiment with that at some point, but in principle, we don't see a reason why it shouldn't work. Okay, I think these are the questions I see, unless I'm missing anything else. So if you have any other questions, feel free to contact me through email. I will be happy to address. Thank you very much for attending and listening and for the questions.